All right, if you are in the chat on Zoom or whatever, please type something in the chat to let me know that you are present. For those of you that are physically here, I will be handing out the roll sheet. This is a reminder, your exam 2 will be given on Wednesday, and it will cover steady state sinusoidal circuit analysis and filters. So it will not cover what we're covering in class today, which is steady state sinusoidal power analysis. We are going to start with instantaneous power and average power. Just realized I left some of my notes upstairs, but I think it'll be okay. All right. So let's say that I have a system like so. Or this is some arbitrary load. IL of t, like so. If Vs of t is of the form Vm cosine omega t plus theta v, then we know that the voltage drop over our load should be of that same form. So let's call it VL of t is equal to Vm cosine omega t plus theta v, and IL of t will be of the form Im cosine omega t plus theta I. The instantaneous power absorbed by our load, PL of t, will be VL of t multiplied by IL of t. So P is equal to I times V, as per usual. I'm going to be applying the following trig identity that says A1 cosine angle 1 multiplied by A2 cosine angle 2 yields A1 times A2 times 1/2 cosine angle 1 minus angle 2 plus cosine angle 1 plus angle 2. And so this is going to give me 1/2 Vm Im cosine theta v minus theta I plus 1/2 Vm Im sine. Sorry, that's wrong. That is wildly wrong. Sorry about that. Cosine twice omega t plus theta v plus theta I. So I'd like us to look at this expression. It's big and it's ugly, but it's actually quite useful. And it actually shows us quite a bit of what's going on as well. Okay. So one thing that I want to point out here is that Vm is the magnitude of the voltage Im is the magnitude of the current. Theta V and theta I are the phase angles of the voltage and current respectively. Meaning, this equation down here does not have any phasors in it whatsoever. We would use phasor analysis to get those quantities, but there are not phasors inside of this equation. So if you put phasors inside of this equation, you're going to get the wrong answer. So I just want to be very, very clear about that. All right, so the voltage drop over our load, the magnitude of the voltage drop over our load, the magnitude of the current flowing through our load, the phase angle of the voltage over our load, and the phase angle of the current flowing through our load are all constant quantities, which means that this first term is a DC quantity, and this second term is an AC quantity, right? Meaning it oscillates in time. So generically, we might observe that as a function of time, our power might look something like this. Where we have an oscillation as well as a DC offset. So that's our DC level. And this is the amplitude of our AC term. Okay. As it turns out, and I'm trying to decide whether I want to waste the time of mathematically proving this or not, since we proved it in Engineering 221, the DC term represents the average value of the instantaneous power. Okay. Hopefully you can see that from the graph. Exactly half of the time, since we have a sinusoidal response here, exactly half of the time our instantaneous power is above that DC offset level, and exactly half of the time our instantaneous power is below that DC offset level. And so since it's a sinusoid, it's pretty easy to see then that that DC level is the average value of the sinusoidal function. If the DC portion weren't there, then the average value of the sinusoidal function would be 0. We can use this generic representation and come up with some expressions for the instantaneous and average powers delivered to resistors, capacitors, and inductors. So if our load is purely resistive, meaning that the impedance of the load ZL is equal to R plus J0 ohms, so it's purely real, then we know that, excuse me, that's not theta, that's a bad job of it. Theta V is exactly equal to theta I. Remember that we proved that when we developed our phasor relationships for resistors. And so from this, the instantaneous power absorbed by a resistor is going to be 1/2 Vm squared over R times 1 plus the cosine of twice omega t plus twice theta V. And we could just as easily write this as 1/2 Im squared times R times 1 plus cosine twice omega t plus twice theta I. So that allows us to determine the instantaneous power absorbed by our resistor, only knowing the phasor voltage drop across the resistor, or only knowing the average, excuse me, the phasor current flowing through the resistor. If we wanted our average power, P, capital P, resistor average, what would that be? What's the DC portion of either of these terms? Yeah, right. So that would be 1/2 Vm squared over R, or 1/2 Im squared times R. All right. So that is resistors taken care of. Hopefully everything's okay. Notice this is the exact same thing as our DC relationships, except that they're multiplied by a factor of 1/2. Now, for an inductor, all right, so if our load is purely inductive, meaning that the impedance of the load is R plus, excuse me, 0 plus j omega L. Bring for it here. Ohms. What's the relationship between the phase angle of the voltage and the phase angle of the current in an inductor? Anybody remember? If not, we can take a minute to derive it. Which one is plus 90 to the other one? It's going to be plus or minus 90. It just depends on which one is which. All right, let's derive it real quick. So we know that Vm angle theta V is equal to j omega L times Im angle theta I, right? That says voltage phasor is equal to the impedance of the inductor multiplied by the current flowing through the inductor. So that's just good old Ohm's law. So from this, we can see a couple of things. One, the magnitude of the voltage phasor is equal to omega L times Im if we wanted to go that route. Or we could see that the magnitude of our current phasor is Vm over omega L if we wanted to go that route. We also can see that theta V is equal to theta I plus 90 degrees, and therefore theta I is equal to theta V minus 90 degrees. Everybody understand how I got these relations? Nothing too wild or crazy here. Okay, so the average power absorbed by an inductor then, so P, and I'm going to do IND as a function of T. I can't do L because I used that for load earlier, so that's why I'm having to write these things out. All right, so we're going to have 1/2 times V times, 1/2 times the magnitude of the voltage times the magnitude of the current times cosine theta V minus theta I. We're going to simplify that stuff in a second, but we really need to pay attention to the cosine theta v minus cosine theta I portion, okay? So theta v is theta I plus 90 degrees. So if we have theta v minus theta I, that is theta I plus 90 degrees minus theta I. Or we just have the cosine of 90 degrees. What's the cosine of 90 degrees? It's 0. So that means that the average power absorbed by an inductor has to be 0, okay? So that first term is going to entirely go away, and we're going to be left with, so let's see, it's 1/2 the voltage times the magnitude of the voltage, so that's going to be Vm squared over omega L times the cosine of twice omega t theta v plus theta I plus twice theta v minus 90 degrees. So this gives us everything in terms of the phasor voltage over our inductor. We could also say that it is going to be 1/2 Im squared times omega L cosine twice omega t plus twice theta I plus 90 degrees. And then our average values again, P average for an inductor is 0. Everybody on board with this? All right, so lastly then we have if our load is purely capacitive. Which means that the impedance of our load is 0 minus J over omega C ohms. Doing it in rectangular form, where I'm explicitly noting that we expect the reactance of the capacitor to be negative. We know that Im angle theta I is equal to J omega C times Vm angle theta V, which tells us that the magnitude of our current is omega C times Vm, or alternatively, the magnitude of our voltage is Im divided by omega C. We also know that theta I is equal to theta V plus 90 degrees. So therefore, theta V is theta I minus 90 degrees. Everybody okay with what I've done there? Anybody got any problems or anything? If not, we can see that our power, instantaneous power for a capacitor. So we're going to have the same bit here again. We have cosine theta V minus theta I. So that's theta I minus 90 degrees minus theta I. So we're looking at the cosine of negative 90, which is also 0. So we know that there's not going to be a DC term. So from this, we're going to have 1/2 Vm squared omega C times the cosine of twice omega t. So let's see, theta V twice theta V plus 90 degrees, and alternatively expressed purely in terms of our current quantities, that would be Im squared over omega c cosine twice omega t plus twice theta I minus 90 degrees, where we know that our average value, P average for a capacitor, is 0. So I believe we have sufficiently covered instantaneous and average power, both in a general sense. So for a generalized load where it has some mixed inductance, a mixed impedance that contains both a resistive and reactive element, we would use the first equation that we developed. For a purely resistive, then we can break it down into this set of equations where we only need to know the voltage phasor or the current phasor, and we're allowed to calculate everything. For an inductor, we know the average power is 0, and we develop relationships only knowing the phasor voltage and only knowing the phasor current again. And finally, for a capacitor, we have an average power of 0 and an expression for the instantaneous power, only knowing the phasor voltage and only knowing the phasor current. So we should be in a good situation calculating the instantaneous and average power for any possible type of load or source that we might deal with. So everybody good on this. Hopefully it's largely review of what you did in 220. All right, then the last thing that I want to talk about today, and this is going to take a little bit of time, is what's called maximum average power transfer. Okay. All right, so for DC circuits, we could simplify a two-terminal network into a Thevenin equivalent circuit to determine maximum power that can be delivered by that circuit. Delivered by that. So what I mean explicitly, hopefully you guys recall this. Let's say that we had the following circuit where we have a Thevenin voltage source and a Thevenin resistance, R Thevenin, like so. And we want to know the maximum power that could be delivered through an arbitrary load resistance, RO. We know, let me define some stuff here. The voltage drop over our load resistance is VL, like so. The current flowing through our load resistance is IL, like so. And therefore, the power absorbed by our load resistance is simply VL multiplied by IL. And we can get that as, let's see, using voltage division, VL is VThev times RL divided by RThev plus RL. That's just using voltage division. And our current IL, just using Ohm's law, is VThev divided by RThev plus RL. So simplifying this guy, we have our Thevenin voltage squared times RL divided by quantity RThev plus RL squared. So that gives us what the power supplied by that two-terminal circuit on the left-hand side is, or the power absorbed by that load is, for any known value of VThev and RThev, right? Which is just the Thevenin equivalent of our two-terminal network of interest. In circuits 1, we found that the maximum amount of power that can be delivered by that practical source occurs when RL is exactly equal to R Thevenin. And under that case, when RL is equal to R Thev, PL max is equal to 1/4 times V Thevenin squared divided by RL. Hopefully this is ringing some bells from what you guys did in circuits 1, okay? We got that by maximizing this expression for the power, meaning that we took the derivative of this expression with respect to RL and set it to 0 and found out what value occurred to give us our maximum, or what value gave us our inflection point. Just good old calculus-based definition of finding the minimum or maximum of a function, right? We are going to do effectively that same thing, but with an AC circuit, okay? So let's consider that we know what the Thevenin voltage phasor is for a particular circuit, and the Thevenin impedance for a particular circuit. And we are trying to find out the maximum power that can be delivered to an arbitrary load impedance ZL. So here is our phasor voltage VL, and here is our phasor current IL. Now, we already know that the average power absorbed by my load resistance is going to be 1/2 VL, so the magnitude of phasor voltage VL times the magnitude of the phasor voltage, or excuse me, phasor current IL times the cosine of theta VL minus theta IL. That is our average power based on what we just learned a couple of minutes ago, right? So what I am going to do is develop expressions for the magnitude of the phasor voltage over our load, the magnitude of the phasor current passing through our load, and the cosine of the angles of the voltage and current respectively, okay? So hopefully by inspection, we can see that the phasor voltage drop over our load here, just using voltage division, is going to be our phasor voltage V Thevenin times our impedance ZL divided by Z Thev plus ZL, right? Just voltage division. Now, in order to get the magnitude of this guy, I'm going to break this up and express my impedances in rectangular form. So what I mean by that is I'm going to have in my denominator R thev plus J X thev plus RL plus JXL. So that's just me splitting up those two impedances into their resistive and reactive portions. In my numerator, I'm still going to have my phasor Thevenin voltage, but this is going to be multiplied by RL plus JXL. So to take the magnitude of this guy, is going to look something like this. The magnitude of V thev times the square root of RL squared plus XL squared. So just to be clear, all I've done to take the magnitudes of these portions, let's look at our numerator and everything else to kind of follow suit. I want the magnitude of this complex number, right? It has a real part that is RL, and it has an imaginary part that is XL. We know that the magnitude of a complex number is the square root of the real part squared plus the imaginary part squared. So that's exactly where this came from. For this guy down here, I just added the real parts of my impedances together and the imaginary parts of my impedances together, and then took the magnitude of that whole quantity, okay? And then for the magnitude of my voltage, I just say I want the magnitude of the voltage. So I throw away the phase angle portion. I can do a similar thing for the current. So my phasor current by inspection, so this is just using Ohm's law, is going to be my phasor voltage V thev divided by Z thev plus ZL, which looks like R thev plus J X thev plus RL XL in my denominator, and then I just have the magnitude V thev here in my numerator. I'm going to take the magnitude of it in the exact same fashion that I took the magnitude of VL. And so that is going to give me in my denominator R thev plus RL quantity squared plus X thev plus XL quantity squared. And then up here, I simply have the magnitude of my Thevenin voltage. So I know what my magnitude of my voltage drop over the load is. I know what the magnitude of the current flowing through the load is. So the last thing I need to figure out is some relationship that expresses the cosine of theta V minus theta I, okay? Now, hopefully you guys recall that an impedance can be expressed in both rectangular form, which is what we've been doing, and polar form as well, okay? So if I were to plot an impedance on a complex plane, it might look something like this. Here is my real axis. Here is my imaginary axis. And here is my, let's say my load impedance, ZL, okay? Where the projection onto the real axis is the resistance, and the projection onto the imaginary axis is the reactance, right? Just a complex number. Obviously, we have an angle here that I'm going to call theta ZL formed between our impedance and the real axis. Who can tell me how theta ZL relates to theta V and theta I? Anybody got any thoughts? Yeah. So if you recall, impedance by definition is phasor voltage divided by phasor current, which means we have Vm angle theta V divided by Im angle theta I, gives us a magnitude of Vm over Im with an angle of theta V minus theta I. So that theta ZL is the exact same thing as theta V minus theta I. So, recognizing that, cosine of theta V minus theta I is going to be what? It's the adjacent divided by the hypotenuse, right? Good old trig. You guys took trig in high school probably, right? So the adjacent bit here is RL, and the hypotenuse is just the magnitude of my impedance, which is the square root of RL squared plus XL squared. Everybody okay with that? Anybody got any problems with how that was derived? So now, yeah, we're going to finish up pretty early. So now what we're going to do is just put these three parts together, right? We know that the average power is just 1/2 times the magnitude of the voltage times the magnitude of the current times the cosine. And so from this, we get 1/2 times so this should be the magnitude of V thev up here, and then the square root of RL squared plus XL squared here. So that's the magnitude of our voltage, the magnitude of our current, here we have just the magnitude of V thev. And then lastly, we have our cosine theta V minus theta I, which just looks like RL divided by the square root of RL squared plus XL squared. All right, so we can notice a couple of things. First, the denominator of our voltage and the denominator of our current are the same. Since we're multiplying them together, that's going to get rid of that square root sign. We can see that we have in the numerator of our voltage a factor of the square root of RL squared plus XL squared. And in the denominator of our cosine term, we have that exact same quantity. So those guys are going to cancel each other out. So this guy takes care of this guy. And what we are left with is 1/2 R thev plus RL quantity squared plus X thev plus XL quantity squared in our denominator. Up here, we have the magnitude of our Thevenin voltage, V thev squared times RL. So, what does the reactive portion of our load do? If we wanted to maximize this function, right? This is our function that we are trying to maximize in order to determine what value of ZL causes the most amount of average power to be transferred to that load or be supplied by that source, okay? So X thev plus XL quantity squared is in the denominator, which means if we have any reactance whatsoever, our average power goes down, right? The average power delivered to the load goes down if we have any reactance. So for maximum average power transfer to occur, that means that all of the reactance needs to go away, or XL is exactly equal to negative X step. Does that make sense? All right. So from this guy, we know that XL is equal to negative X step to cause maximum average power transfer to occur. So under that constraint, let's rewrite our equation. Looks like 1/2 times magnitude of our Thevenin voltage squared times RL over R Thev plus RL squared. Other than the factor of 1/2, this should look reasonably familiar. Let me scroll up and prove it to you. It is the exact same expression that we maximized in circuits 1, okay? So we know what value of RL makes maximum power transfer occur when X Thev is equal to, or excuse me, XL is equal to negative X Thev. We know that RL has to be equal to R Thev as well, okay? So from this, for maximum average power transfer to occur, we need ZL is equal to R Thev minus J X Thev, which is the same as the complex conjugate of our Thevenin impedance. Under this constraint, our maximum average power transfer is 1/8 magnitude of our Thevenin voltage squared divided by only the resistive portion of our load impedance. Excuse me. This should be R Thev. All right. Okay, so that's what I wanted to talk about today. We finished half an hour early, which means we can spend the next half an hour talking about the test if you guys have any questions or anything. Or we can knock off or whatever floats your boat. Yes, you do get a equation sheet. I don't like to call it a cheat sheet because cheating has a negative connotation here. So you do get an equation sheet. Your equation sheet is a standard 8.5 by 11 sheet of copy paper or whatever you want to call it. It just needs to be handwritten, and you can do the front and the back. Okay. So I would suggest putting on there I would write down just as a reference how to do voltage division, how to do current division, how to do source transformations and things like that. Maybe an example of using superposition as well, just if it's something that you're not super familiar with. So that would be one side, is just the basics of how to do steady state sinusoidal circuit analysis. Also obviously put on there how to convert from the time domain to the frequency domain and vice versa. So meaning, you know, how to convert impedances, capacitance and inductance and resistance to their equivalent impedances. Put some trig identities for switching from sine to cosine on there. I feel like I'm probably going to be a jerk and make you do that. Try to trip you up with something like that. Although I don't know how much of a jerk it is if I tell you I'm going to do it. But anyway, so that's the steady state sinusoidal stuff. Then the other side of your sheet should just be the filter stuff. So for the filters, I would put on there transfer functions, phase response, frequency response or the magnitude response, as well as 3 dB cutoff frequencies and resonant frequencies for the second order filters. Your filter circuit question, it'll just be one question, will literally be something that we derived in class, but with numbers. So it won't be anything remotely difficult. It'll literally be straight from the equation sheet to the answer. Also, just as a heads up, all of those videos have been uploaded to YouTube and Moodle over the weekend. I think I finished them all on Saturday. So if you're missing any of that filter stuff, it's there. What else? Grades for the last test. Fantastic question. Since this upcoming Friday is the drop date, I need to make sure to have your tests graded. I did not get them graded over the weekend because I was doing all my preparation for the senior advising and all that kind of good stuff. So I will have your grades to you hopefully on Wednesday, but by Thursday at the absolute latest, so that you will have your test grades, you'll have your homework grades and all that kind of stuff, and you can make an informed decision as to whether or not you need to drop the course on Friday. Should you need to drop the course, which I don't anticipate anybody needing to do that, I feel like I'm not making this crap wildly stretch, but some of you may disagree. But if for whatever reason you do need to drop the class, Circuits 2 is offered again over the summer, and you could do it in person or online, I don't really care which, so that you could keep caught up for the fall. So don't think it's going to be necessary for any of you guys, but haven't graded your test yet, so I could be wrong. We'll see. What else? I'm going to post that today. I apologize for forgetting about doing it. Yes, I'll put that up today. The filter homework that you're going to have is significantly more difficult than you should expect to see on the exam. Like I said, the exam will be something that I will give you a basic second order filter of some sort and ask you to give me the magnitude response or the phase magnitude response or phase response, or ask you to calculate what the cutoff frequencies are if I give you values of RL and C, that kind of stuff. Nothing remotely difficult. Literally, if you write down the equations, you're good to go. Yes, sir.
Are we going to be doing our design problems?
Okay, fantastic question as well. I do need to put those up. I'll probably get some of, at least one of those up soonish. So here's the deal. Here's how this is going to work. If I continue to forget to do it, you get all of the credit for doing none of the work because you did exactly as much as I asked you to do. So
I should never ask you again.
I'm not saying that, but yeah, that's how I wound up doing it last year. I got to get a bit better organized. Yeah. Another option, because I asked you guys to design something on the first test, I'm going to ask you to design something again on the take-home portion of the second test, and I will also ask you to design something on the take-home portion of the third test. I could just as easily just say, that's your grades on those problems constitute your design grade as well. I will likely lean towards the, I forgot about it. That's what I did last quarter. Like I did give design problems on each of the tests, but forgot to give an official design problem. And so I just gave everybody that full 10% because I forgot. So to be consistent, I may conveniently forget. So don't tell anybody important. Any other questions? Yes, ma'am. So I will get the in-class portion done before. So you have to decide whether or not to drop by close of business on Friday. I will get you your in-class portion of those grades sometime before 5 p.m. on Friday. So you will at least have that 70% of exam 2 to know as well. Right now, most of my Thursday is open because not a whole lot of people are scheduling advising over Zoom because I don't come up here to class to campus on Thursdays. So it looks like I have most of Thursday available to get those graded. If not, I'll just stay up that night and piss my wife off and just get it done. So it is what it is. Any other questions? In MathCAD, can you? Absolutely. I believe there is now a video of that up. When did we cover that? Last Friday? Is that right? Yeah. So the video for okay, so if it was Monday, then the video for 419 should have it. If not, it's the video for 416. But there is a video up since the material from our last test, solving a system of equations with complex numbers in it using MathCAD. I have not done that yet. I'll get around to it, but I don't feel like that one is super important because you're not going to be asked a lot of questions about doing stuff in the time domain, which is where you would be able to make those comparisons, if that makes sense. So it is kind of a last ditch effort to check your answers, but I don't feel like the steady state sinusoidal questions that I'm asking are hard enough to super merit that kind of thing. So I will get one up hopefully before the exam on Wednesday, but again, in the grand scheme of things, it's such a small portion that I'm not super concerned about it. Got all the other stuff up, so. All right, what else? All right, see you guys for your tests on Wednesday, because today's totally Monday. I know what day of the week it is.